Today I'll be talking about MrLazy, which is a system that tracks fine-grained data dependencies or lineage in Hadoop MapReduce, and it uses this information for audit and information flow control. So why do we need audits in the cloud? So many organizations have started to publish their internal datasets to third parties, and potentially these datasets have sensitive information. So we want to make sure that this process is being done according to data policies and data sharing policies. So to give you an example, so the NHS in England is starting a data sharing scheme where they'll expose anonymized patient records to approved researchers and organizations. While the benefits are huge in data sharing for the medical care, but obviously the implication of data leakage is serious. So we want to make sure that for example, patients who opt out of data sharing, that the system is not actually exposing their records to third parties. And it doesn't have to be malicious. It can actually happen accidentally. For example, the England team sheet of a recent friendly game had passport numbers along with the player names, right? So obviously the system should deal seamlessly and automatically with these situations. And information flow control has been proposed as a potential solution. Information flow control works by defining a metadata, like a sensitivity tag, to your record, and you propagate that sensitivity tag along with your record through your computation. And you actively check rules and policies at each processing step. While that solves your problem, the fact if you want to apply information flow control for big data systems, that would potentially cause large overheads because you need to deal with additional information and you have to continuously check for policies at each processing step. But we have noticed that many of your computations happen already in-house. So by definition, there isn't really the notion of data leakage. For example, if you are producing some results for your manager or for other departments, that's okay. But once you decide to publish some results to the outside world, now you need to make sure that you do that according to your data sharing policies. And the way we propose to do that is basically by knowing the history of your data output. And by knowing the history, we can basically compute at a later stage, maybe a week later, as a post-processing operation, what is the sensitivity of this piece of output, and apply whatever rules or policies that you want on demand. And we defined labels as a pretty generic placeholder for any data that you want to attach to your record. For example, a sensitivity tag, privacy, different rules for different countries, or maybe even data quality measures. And we want to enforce policies at the very fine-grained level. We want also to deal with some dynamic properties like users opting in and out of your system, sensitivity lasts for a specific period, or even you have new or modified policies on the fly. And we want to deal with these situations seamlessly. And we take MapReduce as a use case because it's a popular framework that people adopt in the cloud. And just to make sure that everyone is on the same page, I know like you know very well MapReduce, so I don't need to spend time but the user defines two functions, the map and reduce, and the framework makes sure that it's being run as a cluster, and it sends all values related to the same key to the same reducer. So if you want to apply standard IFC on top of MapReduce, for example, if we are counting words, you are probably going to have a tag for your record, and you propagate this tag along your record through your computation, and at each processing step, you check rules and policies. And finally, you have a record and an associated static label. So the fact that we have to deal with additional data and we are continuously checking policies, potentially this is large overhead. So we propose to have a different mechanism. We propose to use lineage as an audit to what has happened in your system. And lineage essentially is an association that links a piece in your output file to the relevant input records. For example, here we are associating the A's and the B's. So to use that concept in lazy IFC, again, with the example of counting words, now you don't have to propagate your additional tags through your computation. And say then that you want to compute the sensitivity of your output. You can use basically lineage as an index to your relevant inputs and basically compute a function that takes the relevant input metadata and computes your output tag on demand. And this can happen lazily. This doesn't need to be performed right after the computation. It can happen maybe like a week later or so when you need it, essentially, when you want to publish some results. And you might have like tons of metadata associated to your records. So the key advantage here is that we don't need to deal with any of this additional data because that would pose additional overhead in MapReduce. And you can think of lineage as an index to the relevant input metadata that you need to compute your output tag. And we have implemented lineage capture at a record level granularity in Hadoop MapReduce. And it doesn't require any change to the user code because we have modified the framework to do so. And we wanted to keep the overheads of lineage capture as low as possible. And the way we achieved that is basically by treating map and reduce tasks separately. But now you might require a post-processing ad hoc job that links the map and reduce lineage files to produce a final association between your output back to your input. And so far, I've talked about record level visibility. But as I said, you might need sub-record enforcement of policy because in a record you have sensitive and non-sensitive information. For example, with the England team sheet, you had passport numbers as sensitive information. But if your task is just using the player names, for example, if you are reading a record and using part of the field that corresponds to your to the name only, that process is okay. And the way we plan to approach that is basically by employing standard taint tracking techniques that would analyze the code, the map and reduce code, and that would basically do the trick. And we have tested a prototype implementation of MrLazy on a local 7-node cluster. And we have used the big data bench suite. And we only here present a simple workload that joins and filter records from customer and order logs from a typical supermarket. So the overhead of lineage capture in this case is around 20% additional time overhead on your main job. And as I said, if you want to enforce policies, you might need a post-processing step that constructs the final lineage. But this process is basically an ad hoc job that can run in the background or at a later stage. So it doesn't really affect your main job runtime. And as we are keeping lineage at a record level, so potentially there is a storage requirement, non-negligible storage requirement for the system. And in that specific case, it's around 50% of your output. But we can cap the overall storage requirement of the system by basically deleting lineage for files that are not expected to be used. And in this work, basically, what we argue for is that lineage is a trade-off for computation time, as I'll show you now. So let's try to apply typical policies for data sharing. For example, if 5% of your users opt out of data sharing. So MrLazy would deal with the situation by basically looking at the output data and trying to identify records that are relevant to these 5% of the users and basically omitting them from the output. And because we have lineage, which is a dependency link or graph, we can do that efficiently. And it runs 5x faster than the simple approach of recomputing everything from scratch, but removing these 5% of the users from your input. Let's check a different policy where you have a more dynamic behavior. For example, the sensitivity of a piece of data lasts for a specific time period. And notice here that the results of your policy enforcement depends on when the query is being performed. And in MrLazy, as we do it just before we publish the datasets, the results are up to date. And again, the performance is more or less similar to the policy one. But we need to take care of other challenges as well. So far, we assumed that map and reduce tasks are stateless. But that's not always the case, and the developer can save some state between records. And the way we plan to deal with this case is basically by inlining additional instrumentation in the map and reduce code to expose the state to the framework, so that lineage is precise. And we need to take care of other special type of queries like the top K queries. And even if you assume that the framework is fully trusted, a malicious developer can leak indirectly some data in the output. For example, if a task outputs a special value when seeing a specific user, for example, user ID, by looking at the output, you can indirectly say whether this specific user is present in the input or not. And there are ways to deal with this subtle data leakage by basically employing differential privacy techniques, which complement the work we are doing. So MrLazy basically is a technique that delays any management of metadata to the point when it's needed. For example, when you want to publish some results. Because if you would apply standard IFC on all your computations, that would cause like large overheads. So we advocate that let's delay this process to the point when needed, and we employ lineage as basically an audit mechanism that enables us to compute output tags lazily. Because lineage is basically describes the data history. And we have shown in our prototype implementation that overheads are not prohibitive, but we are working to bring these overheads further down, and we are planning for a large-scale evaluation. And lineage as fine-grained lineage as a concept can be used for other cool stuff. And we basically experimenting with using lineage as a way to recover missing blocks from failure as an alternative technique to replication. So I guess that's it. Thank you, guys.
You talked about looking at the lineage on doing the MapReduce, and there are apparently separate things that you do on the map side versus the reduce side. Could you talk a little bit more about the considerations you had and why what were some of the things that you actually did in that aspect?
Yeah. So basically, we have decided not to propagate. So basically, lineage is an association that links an output record to the relevant input records. And in MapReduce terms, we define that link as a position in your output file and a position in the input file. So you have a link between position in the output to positions in the input. But we decided not to, in the main job, not to propagate these positions along with your computation because that would pose additional overhead. And that would defeat the initial assumption that we don't want to add additional metadata in your computation. So basically, we separated lineage for map and reduce tasks, but now we need a post-processing step that links or joins these lineage files on the intermediate keys to produce a final association from the output back to the input.
Sorry, I have one other one, not specifically on the algorithm, but on actually using the data. So you talk about the specific records that you have.
Yeah.
Obviously, there's going to be certain subsets of that. Is there an option to look at opt-in and opt-out for the individual record objects or are you only looking at the whole record itself?
You mean fields in your...
Yeah, specific fields where they may say, okay, it's okay to share maybe birthdays for age consideration versus passports, which may not.
So that's basically why we advocate to have enforcement per field as a field granularity. So a record in itself might have sensitive and non-sensitive information, as with the example of the England team sheet, passport numbers are sensitive. So with lineage, you can get up to a record visibility, but we employ taint tracking analysis, static taint tracking analysis that can tell you, obviously you need to specify that this field is sensitive. That would tell you that you have used this field in your computation.
Sorry, since nobody else is asking questions, I have one other question. I deal a lot with cloud and using cloud, data within the cloud across multiple regions around the world. And every country is a little bit different about where the data can sit. For example, in the Netherlands, they don't allow specific data to ever sit outside. They could be in the cloud, but only within the boundaries of that country. What are some of the considerations related to that? Because you mentioned this is tied to the National Institute of Health in the UK, but I'm assuming you're looking at some of the considerations for other countries and some of their regulatory compliance.
That's exactly why I said that we might need to have more than one piece of metadata to your record, right? And now you can start to think about loads of metadata associated to your data, and we provide basically a technique that bounds the cost of computing labels when you have, like, as you say, like probably a tag per country.
Boundaries are a little bit different.
Right,
Yeah.
right. So you need to define like more tags that would be executed just like for this region, and that should be all right because like we just like track data dependencies, right? Which is an index to the relevant input that you have used in your computation.